I have a quick question for you guys. If I have an object and I let it go just before the surface of the earth, say this is surface of the earth, I let it go. What happens? Yes, it will fall. So what will be the acceleration? Will the acceleration be equal to 0 or non-zero? Correct. It will be a non-zero acceleration. Now, the same object, but say it is in a container. Okay. Say it's in a container. And say this is a container, that's where it starts, and the same height and everything. Now my question to you guys is, will it accelerate as and when it falls through the container? And say this container is pretty big. So say this container is pretty big. So now my question to you guys is, will this accelerate or not accelerate? Yes and no. The answer is both yes and no. How can it be both yes and no? That's what we are trying to understand in this video, and through that we'll understand a topic called as terminal velocity. Okay guys, it's quite simple actually. So what is this terminal velocity? Or before that, let's see what happens. See guys, as and when an object goes through the object, right? Or let me ask you this question. Whenever we have any object inside a liquid, what happens? There is one thing is gravitational pull, and another thing is there is buoyant force. This is when it's stationary and stuff. But when it's moving, one more force comes into picture, and that is your, yes, viscous force. Right? Viscous drag. Because of viscosity, we have one more force. The thing is, buoyant force is constant for a given condition. I'm not going to write everything. Constant for a given condition. Given condition. And this is not constant. It actually is it varies with velocity. This varies with velocity. This we have seen in the formula itself, right? Stokes' law and all of that we have seen over there. It varies with velocity. Is it not? Try to recall what is the formula. Of course, guys, this is something that you need to remember. It is 6 pi, your coefficient of viscosity, radius of the spherical object. In this case, I'm taking a sphere, and velocity. So if this is varying with velocity, means it's directly proportional to velocity. It will increase with velocity. There will be a point of time wherein all of this will be equal to mg, and what happens? The net force will be what? When this expression is equal to this, the net force will be 0. If the net force is 0, what will happen to the acceleration? Acceleration will be 0. So the object will stop accelerating. Does it make sense? And that's what we are looking at. So when an object falls through a viscous fluid, the drag force acting on it increases with velocity. We know that. This is explained with, this is of course a particular set of condition. But yeah, this gives you guys a glimpse of what happens when an object is falling through a liquid. As the object accelerates downward, drag and buoyant force gradually increases until sum of these upward forces equals the object's weight. Because we have the upward force and the downward force to be equal, the net force will be 0, and so we see no acceleration. The velocity which causes this is known as terminal velocity. The object then continues to fall at a constant velocity known as terminal velocity. Okay? When we have the weight and the drag force to be equal to each other, sorry, not only drag force, plus your buoyant force to be equal to each other, the net force will be 0, acceleration is 0, and thus we have an object which is falling at a constant or the same velocity, and this velocity is known as terminal velocity. Okay guys, so this is something that we are looking at. So we are going to derive here itself the terminal velocity. So Let's look at the derivation. Now, so we have the free body diagram. We have the downward pull. Then we have two forces. So one is your buoyancy and another is your viscous drag. We can consider up as positive direction. Okay. So when the object reaches terminal velocity, the net force is 0. Right? That's the whole funda. That is, sum of all the forces will be equal to 0 and Vd plus U minus mg will be equal to 0. So simple math, mg is equal to fvd plus u, and we have this to be 6 pi. Again, we're taking a very particular case. This formula I kept writing, and this is your 4 pi r cube volume times of density of the object into acceleration due to gravity. So this is your density of object. Okay, guys. Now, on the RHS also, we have this expression actually. I can explain this as well. Mass is again 4 by 3 pi r cube into g. Oh, sorry. This is density of the liquid. My bad. This is density of the... Okay. What do we generally use? Liquid is... This is liquid. My bad. This buoyant force is because of the liquid, na? My bad. And this is density of the object. Okay. So a bit of rearrangement on all of that. So we have 2s, 3s, 2s. Pi is common. R is common. And we have V is equal to, if I transpose that, it will be 2 by 3 r square rho g minus 2 by 3 r square. Sorry, this is rho. This is, I forgot. Okay. Oh, sorry. On the LHS, we have 3 and coefficient of viscosity. And therefore, V is equal to 2 by 9 r square. We have... Again, guys, please use the symbols that your books are using. My bad, I'm using my own over here. I'm not using standardized representation. So if the density representation is different, please use that. Don't be confused. I'm just going with whatever I came up with over here. So that will give you the terminal velocity, knowing the radius, density of the liquid, density of the solid, acceleration due to gravity, coefficient of viscosity. Knowing all of this will give us the velocity of terminal velocity. Okay, 2 by 9 r square sigma minus rho times of g by eta. I hope I'm right with the symbols. Okay, so quite a small derivation. So let me just summarize once more. So whenever we have any object falling through any fluid, it encounters, of course, provided there's a pull against the fluid, I mean in the direction towards the ground or any direction, doesn't matter. In this case, gravity is the cause of downward pull. Against that, you have buoyant force and you have your viscous drag also causing it to basically oppose that motion per se, right? So there's a point of time wherein all of this upward force and the downward pull will cancel each other out, and the object will start falling at a constant velocity because the net force is 0. And that constant velocity is your terminal velocity, right? And that terminal velocity, we can figure it out with a simple set of math and knowing quite a few expressions and a bit of rearrangement, and you end up with this particular expression. That's it. And by the way, I just want to mention it. This is in vacuum. Say this is on the surface of the moon, so that it's clear. And instead of making it green, let me make it, yeah. Because air also provides the same funda, and you have terminal velocity that can be seen in air as well. So I don't want you guys to miss out that I'm ignoring atmosphere. No, we're not ignoring atmosphere. Atmosphere too has the same effect. This is density of the object, right? Yeah, density of the liquid. Okay.